Howdy, everyone, and welcome to the second part of our look at integrals for E and ln, or involving E and ln. Specifically, we're looking at integrals involving ln. So this is the other side of our combination of looking at exponential and logarithmic functions. This time, the integral is, I would say, not as obvious as it is with exponential functions. It's not as clear what the u substitution is, or more to the point, it's quite clear what the u sub is, but it won't be clear exactly when to use it. So I'm going to try and show some comparisons between when this works and when this doesn't. So without further ado, though, let's get started just by looking at our approach to ln. So so a couple of lectures ago, we saw that the derivative of ln of x is 1 over x. And more specifically, when we wanted to use the chain rule, we had that the derivative of ln of some function of x was 1 over that function times the derivative of that function. Or in other words, the derivative of ln of u equals 1 over u times du dx. Well, we're going to undo this. We're going to take a look. If this is the derivative, then we're going to take a look at the antiderivative, the integral. So since we're considering the derivative, since we're considering that the derivative is ln of x, derivative of ln of x equals 1 over x, then it must be that the integral is the reverse. So the integral of 1 over x dx is ln of x plus c. And here, it's actually ln of the absolute value of x. And the reason for that is a log cannot be taken of a negative number, at least not in the real plane. So, or at least not with real numbers. So that's a bit of an issue. We resolve that just by keeping an absolute value. We'll see how that's going to work with definite integrals later. We'll see that this still will make sense. This will still give us the areas it should give us. So there's no real concern about how this works. This is fine. So anyway, let's talk about what exactly is going on with this integral, because this is hopefully clear enough. If we just had the integral of 1 over x dx, it gives us ln of the absolute value of x plus c. One of the first things that this gives us, though, is this finally fills in the last gap we have for arbitrary exponent, for x to some arbitrary exponent. Our original rule for integration just said that the integral of x to the n dx was x to the n plus 1 over n plus 1 plus c. But we noted that this fell apart when n was equal to -1, because we ended up dividing by 0. So the natural log finally allows us to work around that. After all this time, we finally filled in that very last little gap. And surprisingly, this comes up a lot. If you're working in the hard sciences, or indeed for the majority of social sciences, you're probably going to end up solving exponential problems. And if you're solving exponential problems, you're going to be using logs as well, because that's part and parcel of it. ln is the inverse of e, so it's part and parcel of that entire deal. But if you're working in many disciplines, all hard sciences, and then at least economics, and I'm pretty sure probably others as well, there are going to be times when you want to deal with an accumulation of change, which is an integral, of something that's displayed as a fraction, which means that when we integrate it, we're going to get a natural log. Again, the integral of 1 over x dx is ln of the absolute value of x. So this is a pretty big deal. Filling in this gap is very important. And that also means that for the purposes of, if you ever are going to end up needing to use higher level analytics, moving forward, understanding how ln works for you yourself is also very important. So that's great. That this is, not just an irrelevant topic that we're learning just for the sake of completion. Like that, it is great that this has its uses. Most notably, comes to mind for me is chemistry. Understanding reaction rates, understanding amounts of a understanding amounts of a solution or amounts of reactants that are left, or understanding a reaction rate with respect to those amounts, with respect to those um, comparative molarities. Um, it's entirely built around this form of integration. And if you have a one-to-one reaction, it's going to need natural logs. So that's why reaction rates are that's why you'll occasionally see reaction rates be logarithmic. Because, well, this is this is a way to derive that. Not the only way, but one. Um, so it's again, it shows up. So let's go ahead and take a look at trying to apply this in general, which is going to need U substitution. Because a lot of times we're not just going to have a fraction that's 1 over x. We're going to have a fraction that's 1 over or something over some function. So here, the integral of, we're trying to make a form that creates the integral of 1 over u du. So here, we can also write this as the integral of u to the negative 1 du. So here, the good candidates we have for this, and this is what you want to look for. If you take anything away from the slideshow, take what's in bold print. The good candidates to look for here are any time the denominator in some fraction that's in your integrand is not raised to any additional power. So the denominator itself might have powers in it, like it might be a denominator of x squared plus 2x. But the entirety of the denominator should not be raised to any power besides 1. If that's the case, this might be a reasonable candidate for a u substitution with the intent of creating an integral of the form 1 over u du. So the example I give down below here is if we tried to integrate 1 over 4x minus 5 dx, we're going to end up with a natural log. If we try to integrate 1 over 4x minus 5 all squared dx, we're not. In fact, in the next slide, I'll show you what you get, but this just uses a u substitution, but it creates u to the negative 2, which already falls into our traditional integral rules. No need to do anything with ln. So yeah, let's take a look at comparing these two examples. So here we'll look at the one that's going to result in an ln of x, or an ln of a function first. So our idea would be to make u be the denominator in its entirety. So u equals 4x minus 5. We do u substitution in the normal way, so take the derivative, du dx equals 4, solve for dx, dx equals du over 4. And if we make that substitution, what we end up getting here is 1 over u times du over 4. We can pull out the coefficient. If we do that, du over 4 is the same as du times 1/4. So we can pull out the 1 over 4 or put it in front, do whatever you want, leave it alone. Do this however you want. I like pulling it out because it makes it clear what's in the integral. But you don't have to. You could just leave it in there and just treat it the same way we've treated every coefficient, which is just, don't touch it. Just sits there. It just remains a coefficient. But anyway, what we end up getting is 1/4 the integral of 1 over u du. And here's our ln of u. 1/4 integral of 1 over u du equals 1/4 ln of the absolute value of u plus c. And now we just put the original function back. So 1/4 ln of the absolute value of 4x minus 5 plus c. For the record, the absolute value is often understood. You won't always see people write it, or it's often just left out, or it's often assumed that what you're working with will take positive values, so there's no need for it. If you do leave it out, it's the sort of thing I'm going to comment on but not take points off for. Just so we're clear on what's going on here. But it is important. It is there. And it is worth paying attention to the fact that you can't take the log of a negative number. All right. So anyway, our answer: 1/4 ln of the absolute value of 4x minus 5 plus c, or ln of, or all that, you could say that this is also ln of the absolute value of 4x minus 5 over 4 plus c. Plenty of other ways to write it too, for the record, because you've got all sorts of log rules about how you can handle coefficients and turn them into exponents inside the log, but another time. So let's compare that to the other example I gave, which is where now this 4x minus 5 is squared. So here, we're going to make the same substitution. U is still 4x minus 5. Du dx is still 4, dx still equals du over 4. We're getting the exact same setup here, but now we have 1 over u squared times du over 4, which, if we rewrite this so that everything's in the numerator, if we rewrite this to get rid of our fraction, at least inside the integral, we're going to leave the 1/4 outside. But if we rewrite this, what we get is 1/4 times the integral of u to the -2 du. The exponent of -2 rather, for u just means that we can use our original integral rules. There's no need for a natural log here. Add 1 to the exponent, divide by the new exponent. So adding 1 to -2 gives us -1, divide by -1, so we get 1/4 times u to the -1 over -1, which is the same as, plus c, which is the same as -1/4 times 4x minus 5 to the -1 plus c, or -1 over 4 times 4x minus 5 plus c. Plenty of, again, multiple ways to write this. Any of them are fine. So this is the idea, is making a u substitution of what's in the denominator and then working from there in order to try and create an integral of 1 over u du. If we have more complicated denominators, so something like this, where now we don't just have something linear in the denominator, we've got like x cubed minus x. Creating an integral of this form, the form 1 over u du, can absolutely still happen, assuming the numerator has a constant multiple of the derivative of the denominator, which then cancels in the substitution process. So that's the thing you want to look for, is, do you have a fraction with a denominator that is not raised to any other power as a whole? And is the derivative is some constant multiple of the derivative of that denominator in the numerator? If both those things are true, then a simple u substitution to create this form is possible right away. No further work required. Substitute the denominator and complete it from there. So obviously that means that your assignments tonight, for the most part, there is one question that's different, and I kind of highlight that in the assignment, but your assignment regarding this will have this be the case. But yeah, this is what you're looking for. So here, let's see what happens. Again, this is a prime candidate. The denominator is not raised to any additional power. It's just a denominator that needs to be resolved. The numerator is a constant multiple of the derivative of the denominator, so we're going to be in good shape. So here, our substitution is the denominator, x cubed minus x. Du over dx equals 3x minus 1, gives us isolating dx. Dx equals du over 3x minus 1. We can factor a 2 out of 6x squared minus 2 and get 2 times 3x squared minus 1. So our integral becomes 2 times 3x squared minus 1 over u times du over 3x squared minus 1, and we can see that these cancel. And once we cancel those, we get 2 times the integral of 1 over u du. We've got that form that we want. So here, the moment we have this form, that means it's an ln. So this becomes 2 times ln of the absolute value of u plus c, and then we just put our original function back. So 2 times ln of the absolute value of x cubed minus x plus c. So let's take a look. So this is kind of how we're going to resolve this. So let's take a look at what happens with boundaries. Again, if we have boundaries, we should complete the whole integral first and then just plug in the boundaries at the end. So even though I'm kind of adding in a step here, this is still the exact same format. You're still trying to do everything you would do normally, just we've added in boundaries. So here, if we had the integral from 2 to 7 of 1 over x dx, the integral of 1 over x dx goes to ln of x, or ln of the absolute value of x. But now we need to plug in 7 and 2. So we get ln of 7. Notice I dropped the absolute value here because 7's positive. So ln of 7 minus ln of 2. I go on to note here that we can actually simplify a little further by using log rules. Log of a minus log of b is the same as log of a over b. Similarly, log of a plus log of b is the same as log of a times b. So things like this are fine for writing, things like this allow you to simplify your answer. It makes it look a little bit nicer. I certainly would happily accept ln 7 minus ln 2. That's fine. It's showing that you know what you're doing. Obviously, this is better because it's more condensed. It's easier to compute. You're less likely to have decimal errors if you actually needed a number. But both are appropriate. By the way, side note, I'm going to comment on this once again. There's no need to make this a decimal. You can leave it as something like ln 7 minus ln 2 or ln of 7 over 2. You don't need to plug this into a calculator. And the reason for that is this is a better answer than the 1 point whatever that this is going to result. I guess this should come out to be something along the lines of like 1.2, I want to say 1.25-ish. Wish I had a calculator in front of me. But yeah, it's better if you just leave it as is, because any answer I write is necessarily less accurate than this, because this is exact. Any decimal is not. So yeah, anyway, moving on. Another important note here, and again, this is just another example that kind of follows the same thing the above follows, but a log of 1 is always 0. So ln of 1 is 0, or log base anything of 1 is 0, in fact. Log base, the only time you might be like, well, maybe not, would be, say log base 0 of 0, but log base 0 has its own issues, so don't worry about that. It's just, not really a thing. Log is supposed to represent exponentials, so a log base 0 obviously has problems. Anyway, log, ln of 1, going back to this, ln of 1 is 0. So what we have here is, if we plug in something like, if we end up with ln of the absolute value of x from 1 to 5, we get ln 5 minus ln 1. This is something that I am a little more concerned about. Please don't leave me an ln 1 in an answer. That's just terrible. So if you get something like this, I really would want to see the final answer just be ln 5. I don't want to see something like ln 5 minus ln 1. That hurts my soul. So so let's talk a little bit, or let's show an example of this, and then I'll move on to just doing a few more examples on a online whiteboard. Once again, with the terrible handwriting that comes from not having a touchpad that I can use, and instead needing a mouse. So, or not having a tablet, I guess. So anyway, let's take a look at this integral. So the integral from 2 to 3 of 3x over 4x squared minus 6 dx. And for simplicity, and because this is what most of you have chosen to do, this is the method most of you have chosen, throughout this problem, we're going to leave the boundaries with respect to x. So even while we're kind of in terms of u, you'll notice that the boundaries are still 2 to 3. Please don't treat that like these are now with respect to u. They're not. You need, before you plug these in, you need to go back to your function of x. All right, so let's take a look at what's going on here. Once again, this is a great candidate for our u substitution that's going to create kind of a form of 1 over u du. And the reason for that is the denominator it's a simple fraction. It's with a denominator that is not raised to any particular power. And the numerator is, in fact, a constant multiple of the derivative of the denominator. So we'll make our substitution. U equals 4x squared minus 6. So du dx is 8. So dx is du over 8x. Or du dx is 8x, sorry. So dx equals du over 8x. So when we plug these things into the integral, we get 3x over u, right? Like this, we just replace 4x squared minus 6 with u. And dx gets replaced with du over 8x. The x's cancel. You get left with 3/8 as a coefficient. So we get 3/8, the integral of 1 over u du. This integral just goes to ln of the absolute value of u. No need for the plus c, right? Because this is a definite integral. So we're not caring about a graph, we're caring about an area. So there's no need for that plus c. It's not relevant for this problem. That's not what we're about. So we plug it back in the original function. We get 3/8 ln of the absolute value of 4x squared minus 6 from 2 to 3. Here, the absolute value is unnecessary because all the values we care about are going to be greater than 0. So you'll see me drop that here. 3/8, plug in 3, we get 36 minus 6 is 30. Plug in 2, we get 16 minus 6 is 10. So ln 30 minus ln 10. And now I do use the log rule from the last slide saying that log of a minus log of b is log of a over b. So if you left your answer like this, I'd accept it, but it sure as heck looks better like this, because even then it simplifies further because that 30 over 10 cancels to 3. So you get 3 ln of 3 over 8. So yeah, this will be just slightly over 3/8 because ln 3 is slightly over 1. So yeah, that's about it. So kind of some final notes here. Once again, you should generally be trying to use this when you have the integral of a fraction where the denominator is just not raised to another power. And most of the time, the whole of the denominator will be your choice for u. Also, as a side note, we're not integrating ln of x. We're integrating a fraction that creates ln of x. The integral of ln of x dx is a thing, but that's more of a Calc 2 thing. You need something called integration by parts to resolve it, which is the opposite of the product rule, whereas u substitution, which is what we are using, is the opposite of the chain rule. So without further ado, we'll go through just 3 more problems here and just kind of show what's going on. So let's go ahead to a whiteboard. So let's start with the, whoa, okay, lag. Let's start with the integral from 1 to 4 of 3x to the, I want that to be a 1, please. 3x to the 1/2. Wow, that is actually appalling. All right, we're going to pretend that that's a reasonable 2 and then make it better. But we're going to get 3x to the 1/2 plus 4. And this is going to be over x to the 3/2 plus 2x. So once again, what we're going to do here is our u substitution is just going to be the denominator. So, oop, that's not what I wanted to do. Oh, that doesn't work how I hoped it worked. I was hoping I could just copy that. Turns out not. Um, so if we make our u substitution here, what we get is we just get u equals x to the not a question mark. I hate mice. X to the 3/2 plus 2x. And what this is going to give us if we take the derivatives, if we take the derivative is we're going to get it needs to be a d. We're going to get du dx is equal to 3/2 x to the 1/2 plus 2. And here, if we have 3/2 x to the 1/2 plus 2, that's exactly half of what's in the numerator up here. This numerator can be written as 2 times 3/2 x to the 1/2 plus 2. So let's see what we get here. We end up getting the integral from 1 to 4 of, make it 2. We get the integral from 1 to 4 of 2 times 3/2 x to the 1/2 plus 4, or plus 2 rather. And this is just over u times du over 3/2 x to the 1/2 make the 2 plus 2. And here, what ends up happening is, wow, spectacular. This and this will cancel. So we end up getting the integral. We end up getting the integral from 1 to 4 of 2 over u du. So we just end up getting 2 ln of the absolute value of u evaluated from 1 to 4. And here, if we put things back, what we end up getting is we will get, we will end up getting 2 ln of x to the 3/2 plus 2 x evaluated from 1 to 4. And if we plug 4 into this, what we end up getting is, what we end up getting here is we'll get 8 plus 8, which is 16. And if we plug if we plug 1 into this, we'll get 1 plus 2, which is 3. So we get 2 times ln of 16 minus ln 3, or 2 times ln of 16 thirds, or any other kind of any other combination of using these log rules that you choose to use. But yeah, that's it. So let's take a look at another example, and we'll go ahead and try this. Let's take a look at the the integral of cotangent of x dx. Here, one of the wonderful things that we can do is we can actually rewrite cotangent as cosine. You know what? The text is way better. We can actually rewrite this as cosine over sine. So cotangent of x is cosine x over sine of x. So here, what this means that we get is we're actually looking at the integral of we're actually looking at the integral of cosine of x over sine of x dx. So what we're going to end up here, what we're going to end up with here is we once again have a denominator that has its derivative in the numerator, and here the denominator is actually otherwise left alone. So here, what we could do is we could just say u equals sine of x, and that tells us that du dx is equal to cosine of x. And what that does for us is it also tells us that dx equals du over cosine of x. So what we end up getting here is when we make this substitution, we end up getting something that looks like this. We end up getting cosine of x over, let's just put another one here. We end up getting cosine of x over u times du over cosine of x. And as before, cancel what you can cancel, and we just have 1 over u du, or du over u, or whatever you want to call it. And so this just ends up becoming ln of u plus c. And if we put this back, this ends up just being ln of sine of x plus c. And we're done. So it turns out the integral of cotangent is ln of sine of x, or ln of the absolute value of sine of x. Pretty interesting thing there is that this also actually gives us one of the trig integrals that we're missing. It also gives us tangent. This does not yet give us actually it does also give us secant and cosecant as well, but that requires a little more clever algebraic manipulation. It does actually give us those as well, but requires a little more manipulation than I care to do. But yeah, so this is another thing we can do, right? It doesn't just have to be polynomials; it can be trig functions too. So very last thing, and this is an aside, if you're feeling comfortable with what's going on, or if you're looking for kind of more examples of use sub, or if you're just looking for making sure that you understand what's going on, what's coming up, this last thing, isn't really to do with that. This is just justifying that the absolute value works out how it should. So let's just briefly take a look at one more example here, which goes from -4 to -2 of 1 over x dx. For the record, by the way, 1 over x looks like this, roughly. If I could draw better, it would look nicer. So going from -2 to -4 would be, you know, this region here. So this region is below the x-axis, so we should be getting a negative number when we actually look for this answer. So if we've done something right, we should be getting the negative version of going from going from x equals 2 to x equals 4, just, you know, negative. So let's see what happens. Well, the integral here is relatively easy. 1 over x dx is just ln of the absolute value of x. So, wow, spectacular. Again, evaluated from -4 to -2. And now when we plug these things in, what we get is ln of the absolute value of -2 minus ln of the absolute value of -4. But obviously the absolute value of -2 is just, obviously the absolute value of -2 is just 2. Similarly, the absolute value of -4 is just 4. So here we end up getting ln2 minus ln4. ln4 is larger than ln2, so this is negative. And not only that, but if we had gone the integral from 2 to 4, positive 2 to positive 4, which would be, you know, this region from here to here. Let's make that a little more. Yeah, there we go. Let's say it was from there to there. This region and this region are the exact same region, just one's over here and above the x-axis, one's over here and below the x-axis. So if we had gone from 2 to 4 instead, we'd have had the same answer, but these would be reversed. So perfect. This is exactly the negative version of this. For the record, this is also equal to, as you know, one final side note, this is also equal to ln of 2 over 4, in other words, ln of 1/2. The log of a number that's between 0 and 1 is always negative. Because, assuming that you have a base above 1 anyway. The log is negative. So ln base, you know, ln is base e, so ln of a fraction below 1 is always going to yield a negative number. So this fits. So yeah, that's about all I wanted to deal with here. So hopefully that's enough in the way of examples. If not, feel free to reach out to me, and I'm happy to go over more. So yeah, until next time.